So far, we have seen half wave rectifier. And if you observe the ripple factor in half wave rectifier, it is the amount of unwanted AC by the DC component. So our main intention is to convert AC signal into DC. While converting AC into DC, we are finding some unwanted AC component. So this unwanted AC component should be as much low as possible, and the output DC should be as much high as possible, which means the ripple factor should be as much low as possible. But what we are getting here, as much low as possible, means ideal value of ripple factor is 0. In half wave rectifier, how much is the ripple factor? It is 1.21, which is extremely high. Okay. Why it is happening so? Because of the presence of this unwanted AC. And next one. So this is one drawback. And the next one is conversion efficiency. So you are converting AC signal into DC signal. So ideally 100 conversion efficiency is 100%. Practically it is not possible. But in this particular case, what we are getting 40.6%, which is very less. So the conversion efficiency is less. To improve these two things, means to reduce the ripple factor and to increase the conversion efficiency, we are going to the next circuit, that is full wave rectifier, and in which we have two categories. In full wave rectifier, we have two categories. One is center tapped full wave rectifier, and the second one is bridge type full wave rectifier. Okay, let us start with this center tapped full wave rectifier. Okay, so our concern is to reduce the ripple factor to improve the conversion efficiency. Of course, there are other factors like regulation. Regulation also should be very low. We discussed in half wave rectifier. Okay, peak inverse voltage should be as much low as possible. Okay, all these things. We'll see here how the things will be. And coming to the circuit, center tapped full wave rectifier circuit is appearing like this. So you are all well aware of this center tap. What it does, it splits the complete secondary voltage, right? The voltage between these two ends into two equal halves. Okay, with respect to the center tap, whatever the voltage you have between one end of the center tap to the ground, the same voltage you can see from other end of the center tap to ground. That's what we can. Okay, then why did I write two circuits? See, here there are two notations we generally follow. The first notation, if I take this voltage as Vs, okay, and this is also Vs, equal to equal halves. Okay, there's some meaning. So the total voltage is, right, general in half wave rectifier, what did I write? The voltage between two ends of the secondary winding as Vs. Now, according to this particular notation, the voltage at this point with respect to ground, if I take Vs, then voltage at this point with respect to this other end is also Vs. And along with that, the resistance looking into this particular center tap, one end of the center tap to ground, if I take this as Rs, the same thing I can take here also. So from this end to the other end of the secondary winding, it is also Rs. If that is the case, the total voltage between the two ends of the secondary winding will be 2 Vs, and I can write this as Vs dash. And the total resistance between the two ends of the secondary winding, it is Rs dash is equal to 2Rs. Please do observe this. Okay, and second version. If I take the total voltage between the two ends of the secondary winding as Vs, and the total resistance looking into the secondary winding, the total secondary winding between these two ends as Rs, then one end of the secondary winding and ground, right, between these two, the voltage looking will be if I take this voltage, right, this voltage will be Vs by 2, and the resistance will be Rs by 2. Similarly, voltage at this point with respect to the other end of the secondary winding, this will be Vs by 2 and the resistance will be Rs by 2. This is the difference, because in the exam they may mention the voltage between the two ends of the secondary winding is equal to some 20 volts. Then the voltage at one end of the secondary winding to ground will be 10 volts. That's what you need to observe. And the resistance between the two ends of the secondary winding, if they give 100 ohms, then one end of the secondary winding to ground, the resistance will be 50 ohms. It all. Or sometimes directly they will mention like one end of the secondary winding to ground, the voltage is some 20 volts. Okay, that's fine. Means the voltage between the two ends of the secondary winding will be 40 volts. Okay, this is one very important point. And generally if they mention this is 10 volts, means that might be RMS value. Please do observe this. If they give 10 sine omega t, then peak amplitude will be 10. But if they give 10 volts, means it should be RMS value. Okay. Anyway, in half wave rectifier, we did all those things. I did some problems in half wave rectifier as well. Okay. Now, the same circuit can be even redrawn in this fashion. This is center tap. And both cathodes are joined together. Both cathodes are joined together here. And from that junction, resistance RL is going to ground. Like this. And what about the output? Output will be taken from right to left. Means from the junction of two cathodes to the ground. Right. This is our V output. Let me take this as D1, D2. I'm just following this notation here. Vs and Vs, so that the resistance looking into this terminal is Rs and the resistance looking here is also Rs. This is the notation I am following here. Okay, instead of this notation. And this circuit can be redrawn like this, or this circuit, whatever it is. So we can draw the circuit in this manner as well. This is what I am going to use throughout the analysis of full center tapped full wave rectifier. Okay, see this circuit. This is our center tapped full wave rectifier with the dot convention. Right here, dot is here, means anyway it is plus, it is minus. The dot is here, it is plus and it is minus ground. Done. Then what happens during the positive half cycles? Positive half cycle means this is our positive half cycle and this is also positive half cycle. So the anode of the diode is connected to positive terminal and the cathode is going towards the negative terminal. So D1 is on. And what about D2? The anode is connected to the negative terminal of the supply. So the diode is off. D2 is off. So during positive half cycles, D1 is on and D2 is off. I can write it. So see this here. I can show the same thing. Once D1 is on and D2 is off, D2 acts as open circuit and I can write it. So during positive half cycles. D1 is on and D2 is off. That's it. So this is my circuit. Further, I can just remove this particular part and the same circuit can be redrawn in this fashion. Okay. Both are one and the same. Then how does the current flow? Positive to negative terminal of the source. So the current starts and like this and ends this way. It is flowing through the diode from anode to cathode downwards. And I can take this current as IL. Then how does the circuit is looking like? It is, how does the circuit look like? It is looking like a simple half wave rectifier. Is it not so? So, and taking the secondary coil internal resistance into consideration, I can write IL is equal to Vs by Rs plus diode forward resistance Rf plus the load resistance RL. I can write this as RL. Okay, that's it. So I can write IL is equal to Vs by Rs plus Rf plus RL, or it is Vm sin theta by Rs plus Rf plus RL. So this is further written like Im sin theta, where Im is equal to Vm by Rs plus Rf plus RL. Okay, everything is fine. And here one more interesting point I would like to tell, which I forgot here. See, if current through D1 is this ID1, let me take, and current through D2, it is ID2, which comes like this. And if I take the current through IL, load resistance is IL, then, right, if you take this with respect to this node, what we can write? ID1 plus ID2, it is equal to IL. So IL is equal to ID1 plus ID2. Just see this notation. Okay, both the currents are entering and IL is leaving. If I take the node equation here, anyway, ID1 plus ID2 is equal to I. Right. So please do observe this. Then what about, right, I wrote here IDL. To be frank, what I can write is here ID1 is existing and ID2 is 0. So this current is IL. So IL is equal to ID1. That's it. So that's why directly I wrote IL, nothing else. Or we can even write it like this. This is ID1 and it is IL. So here IL is equal to ID1 plus ID2, in which ID2 is 0, ID1, that is of course equal to Im sin theta. Anyway, we need not worry about it. So in simple, I wrote it directly like IL. ID1 and IL are one and the same. Okay, and here this is what I'm showing here. If you look at the waveforms, it is secondary voltage Vs is equal to Vm sin theta. Its peak amplitude is Vm. And current through D1, I can write ID1. It is like Im sin theta. Period means 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, etc. It is from 0 to pi, means during positive cycles of the secondary voltage. What about ID2? ID2 is equal to 0 from 0 to pi. Okay. And the total current IL, it is equal to ID1 plus ID2, and from 0 to pi it is IL is equal to Im sin theta only. Its peak amplitude, it is Im. Okay. Next. And what about the output voltage? V output is equal to IL into RL. That is Im sin theta into RL. Okay. So it is also looking like some sine wave only. Let me write the V output. And what about its peak amplitude? Im into RL, where Im is equal to Vm by Rs plus Rf plus RL multiplied with RL. That is the peak amplitude. So Vs peak amplitude is Vm, and V output peak amplitude is Vm into RL by Rs plus Rf plus RL. So this is just, it is similar to what we studied in half wave rectifier. Okay, done. Next, during negative half cycles, right? If you take this waveform and during negative half cycles, what we can write? Here I am writing it. Let us take the same diagram. Negative half cycle means we can write it like this. This is our negative cycle, and here also it is negative cycle. It looks like we connected a negative source, right? A negative source means actually the universal polarities of ES are from top to bottom only, no doubt about it. Just as it is looking like the negative source, just to see the direction of the current, I am changing the polarities of the supply like this. Okay. Then what happens to diode D1? Its anode is connected to negative terminal, D1 is off, and D2, its anode is connected to positive terminal of the source, so D2 is on. D1 is off and D2 is on. That's it. Okay, that's what I have shown here. D1 is off and D2 is on. So during negative half cycles, D1 is on and D2 is off. Sorry, reverse I wrote. Let me change it to D2 and this one as D1. Okay. Okay, done. So here what about ID1? ID1 is 0 and ID2 will be flowing. Okay, how ID2 flows? Anyway, the current coming here is ID1 plus ID2. Anyway, this is RL, IL. What comes here? ID2 only comes, and IL is equal to ID2. So overall, how the current is flowing? IL and ID2 is equal to, so we know IL is equal to ID1 plus ID2. So ID1 is 0, so IL is equal to ID. And how ID2 flows? It is starting from, right, positive terminal to, and these are all the universal notations. But for our understanding purpose, to see the direction of the current always flows from positive to negative terminal. So how it is flowing? If you observe, so it comes up, it flows from positive to negative terminal, and it is starting at positive terminal like this, flows through the diode. Next, it is going this way, and here ID1 nothing is coming, and it is coming up to here, and this is IL. It is flowing from top to down. Next, it ends at the negative terminal. That's it. So here also, even though it is a negative cycle, the current is flowing from top to bottom. Means current through RL direction is not, direction of current through RL is not changing. Is it not so? Okay, whether it is a positive cycle or negative cycle, IL direction is from top to bottom. That's what we need to observe. Okay, so look at this circuit. The same circuit can also be written in this fashion. How it is so? Let me take this point as A and this point as B. Okay, so from the one end of the secondary winding to anode of the diode, one end of the secondary winding to anode of the diode, and cathode is connected to the point A. Cathode is connected to the point A. And from between A and B, B is anyway connected to ground and which is connected to the center tap. And between A and B, we have RL. And output is taken polarities from A to B. Output is taken polarities from A to B. Again, it is looking like another half wave rectifier. Okay. So, positive cycles, one half wave rectifier. Negative cycles, another half wave rectifier. In half wave rectifier, what happened is the diode was only one diode which is conducting for only positive half cycles. Negative half cycles, there is no output. But here we can see the current in both positive and negative half cycles through RL. Means we can see output during both positive and negative half cycles. This is the interesting point here. Okay, so how is it flowing? To see, as I mentioned, anyway, right, the reality is, right, okay, just to see the direction of the current, I'm changing the polarities of the supply as it is a negative cycle. The current is flowing like this. Okay, this is our IL or ID2, I can say. Current through RL is from A to B, means current is positive and V output is also positive, even though Vs is negative. Is it not so? Then what is the equation we can write for this IL? To be frank, while writing the loop equation, we cannot change the polarities of Vs. Vs polarities are always from top to bottom here, and here also from top to bottom, top to bottom. In that context, okay, what can we write for IL? You can't write it as Vs by Rs plus Rf plus R. Right here, IL is flowing from negative to positive terminal. If you take the universal notation of Vs, so minus Vs by Rs plus Rf plus RL, which is equal to minus Vm sin theta by Rs plus Rf plus RL. That is minus Im sin theta. Okay, minus Im sin theta means how does it appear? If you take minus Im sin theta, it is something like this. Okay, so from pi to 2 pi or from second half cycle, I can say, right, it is minus Im sin theta is positive. Is it not so? If you take Im sin theta, pi to 2 pi, it should be negative. But what did I say? IL is positive. Okay, how IL is positive? Right, the notation is like minus Im sin theta, and minus Im sin theta is positive, right, when input is a negative cycle, or from pi to 2 pi, minus Im sin theta is positive. Simple thing. So from pi to 2 pi, it is Im sin theta. So 0 to pi, it is IL is Im sin theta, and from pi to 2 pi, IL is equal to ID2, right? It is, how can we write this equation? It is minus Im sin theta. We can't write it as Im sin theta. Okay. So what about overall IL? ID1 plus ID2. So 0 to pi, it is Im sin theta, and from pi to 2 pi, it is minus Im sin theta. Again, positive cycle, Im sin theta, that is from 2 pi to 3 pi, and 3 pi to 4 pi, it is minus Im sin theta. Like this we can write. And what about V output? It is simply Im, right, IL into RL. So it appears in a similar fashion. Or just for our understanding purpose, I am making slight modification. Like this we can write. Okay. Or I can even change this color. Because here this is what I have written, and here I wrote purple color, right, and red color, negative cycles. Okay, just to see some difference. Okay, then this is how we are getting the output current or output voltage waveforms. Then we need to find its average value, RMS value, and RMS value of unwanted AC component, that is a ripple component, from that ripple factor, all those things, right, percentage regulation, efficiency, transformer utilization factor, peak inverse voltage, ripple frequency, all these things, right. And here one thing we can do, already I discussed this, how to find its average value. Okay, you just take the blue color one. Blue color one is like one half wave rectifier. Okay, right, and as I said, right, this is D1 acts as a D1 RL combination acts as one half wave rectifier, and D2 RL combination acts as another half wave rectifier. What is its average value? If you take it, so its average value is Im by pi. And what about its average value? It's a delayed version, but same waveform. Its average value is again Im by pi. And the total IL, it's the addition of these two. So addition of these two signals, the overall average value is also summation of the average values. So it is IDC1 and it is IDC2, and here IDC, it is equal to, right, 2Im by pi. Very simple thing. Average value of this half wave rectifier, red color one, and average value of this another half wave rectifier. So what about VDC? I can even write VDC is equal to, right, whatever we got, it's a peak amplitude. Average value is the highest, right? If our class marks are varying this fashion, then what is the average value? Highest percentage multiplied with 2 by pi. The same way here we can write, it is VDC is equal to 2Vm by pi into RL by RS plus RF plus RL. Directly we can write the answer in this fashion. Okay, without any calculations. Anyway, we will do all these things, right? We can do the calculations and check it. Okay, before that, what is the period of the input signal? It's a period of Vs. It is 2 pi. Okay, and what about the period of IL or V0? IL, it is whatever you have from 0 to pi, the same thing is repeating. So let me write its period as T dash, it is equal to T by 2, half of it. Or I can write here it is pi. And what about the period of output voltage? That is also T dash is equal to T by 2 or pi. Time period is half, frequency will be double. Okay, and according to Fourier series, it is a combination of DC and AC. Okay, what is the DC component? We know DC component, without calculating we can take it as 2Im by pi. Okay, and anyway I will calculate it, show. So how do we write it? IL is equal to Im sin theta. I am defining it over one period for the interval 0 to pi. That's it. So what about IDC? It is a and T dash. I'm writing instead of T dash. I'm writing T dash is equal to pi. Anyway, right, IDC is 1 by T dash area under the function over one period dt. It is equal to 1 by pi integral 0 to pi Im sin theta d theta. Im can be brought outside. It is Im by pi integral sin theta is minus cos theta over the interval 0 to pi. Let us take that negative sign also outside. Minus Im by pi into cos pi minus cos 0. So how much do we get? Cos pi is minus 1 and cos 0 is 1. So ultimately it is 2 Im by pi. That's it. We are getting it. But without all these calculations, just like that we did so. Okay. Just by observing the waveforms, we can write the answer. Right. Alternatively, what I am doing is, right, I am writing just IL is equal to Im sin theta over 2 cycles I am taking over the interval 0 to pi, and it is equal to minus Im sin theta over the interval pi to 2 pi. We can write this. Means instead of defining the signal over one cycle, I am defining it for 2 cycles. Okay. Then what about IDC? It is equal to, instead of T dash, I am taking 2T dash over the interval 2T dash IL dt. 2 cycles now. It is from 0 to T dash by 2 and right, okay, 0 to T dash and T dash to T dash. 2 cycles I am taking. So it is further written like 1 by 2 into T dash, it is pi, or overall 2 T dash is T or 2 pi. And 0 to T dash means 0 to pi, it is Im sin theta d theta. Next, from pi to 2 pi, that is T dash to T dash, it is minus Im sin theta d theta. Okay. I hope you all understand. If you integrate over 2 cycles and in the denominator, we should write the 2 cycles duration. That's it. Further, I can take Im outside, Im by 2 pi, and integral sin theta, it is minus cos theta over the limits 0 to pi. And I am taking this minus sign outside, integral sin theta, that is minus cos theta over the interval pi to 2 pi. So further we can write this way, Im by 2 pi into minus sign, I can take it outside, cos pi minus cos 0. Again this minus sign also, if I take outside, it becomes plus cos 2 pi minus cos pi. That's it. So it is Im by 2 pi into, what do we get? It is minus of minus 1 plus 1 minus of minus 1. Okay. So what is its answer? 4. Right, 4 Im by 2 pi, that is 2 Im by pi. Same result we are getting. Why I am mentioning so means, some people will be thinking of like during pi to 2 pi, next half cycle also it is Im sin theta, which is absolutely wrong. Negative cycles, it is looking like minus Im sin theta, whose value is positive. Value is positive, but the equation is looking with negative sign. Okay, that's very, very important. So it is a bit lengthy procedure, not required, right? Oh, why to scratch your head for 2 cycles, 3 cycles, etc. Just to make you aware of the point, minus Im sin theta, I have done these calculations. If this negative sign is not taken, you will get your answer as 0. That is what you can observe, right? That's it. So we calculated the DC component, IDC. Then what about VDC? VDC is equal to IDC into RL, output DC value of the output. That is 2Im by pi into RL. So, or I can further write it like 2 Vm by pi into RL by Rs plus Rf plus RL. That is VDC. Okay, from this DC component, we can develop the Thevenin's equivalent circuit of a center tapped full wave rectifier with respect to DC. Let us write it. This what we can write. See this. As long as this equation is true, this circuit is also true. See, VDC is equal to 2 Vm by pi into RL by Rs plus Rf plus absolutely we are getting. So this is the Thevenin's equivalent circuit. The resistance of the voltage looking into RL and the resistance looking into RL. This is the Thevenin's circuit. And what about V Thevenin's? It is 2 Vm by pi. And what about R Thevenin's? It is Rs plus Rf. That's it. Okay. Physically, this circuit is not existing. We are developing this circuit from its output voltage equation, DC output voltage equation. Okay. So, IDC and VDC are done. Next, IRMS. RMS value of the total current. It is root main square. It is further written like over one cycle I am taking, not 2 cycles. 1 by pi integral 0 to pi Im square sine square theta d theta. Okay, it is further written like Im square by pi integral 0 to pi sine square theta can be written like 1 minus cos 2 theta by 2 d theta. And further it is Im square by 2 pi. Integral 1 d theta, it is theta, minus integral cos 2 theta, that is sin 2 theta by 2, for the limits 0 to pi. Further, it is written like Im square by 2 pi into here theta limits pi and 0 minus sin 2 theta, it is sin 2 pi minus sin 0 by 2. Anyway, its value is 0 and final answer is Im by root 2. In half wave rectifier, RMS value of the total load current is Im by 2, but here it is Im by, or I can write here Im by root 2, not an issue. I can save some space here. So, further, RMS value of unwanted AC component. That is known as ripple component is given by IRMS dash is equal to, what is the formula? RMS value of the total current square minus IDC square. Okay, it is equal to Im by root 2 whole square minus 2Im by pi whole square. Whatever it is, some value you will be ready. Right. And further, once I know the RMS value of AC component and DC component, I can find the ripple factor. The ripple factor, the first parameter, it is equal to unwanted AC. Again and again I am mentioning, by the DC component present in the output. Unwanted AC, it's always in terms of voltage, VAC by VDC. VAC, it is the product of IAC into RL by VDC, it is a product of IDC into RL. RL cancel. IAC by IDC. IAC, right? And who will use Fourier series expansion and to find all those AC components, etc.? Not required. Just I am writing IRMS dash by IDC. And it is further written like, we are well aware, right? It is IRMS by IDC whole square, form factor square minus 1. IRMS, it is Im by root 2 whole square by IDC 2Im by pi whole square minus 1. And it is, if you do the calculations and all, you will get its value to be 0.48. In half wave rectifier, it is 1.21. In full wave rectifier, it has come down. It's not half of half wave rectifier, it is a value node, so square root, some nonlinear equations and all. After calculations, you can see 0.48. This is better compared to half wave rectifier. We have reduced the ripple factor. Means we improved the DC level and reduced the unwanted AC level. So ripple factor we have got. And the second parameter is the percentage radiation. It is given by VDC no load minus VDC full load by VDC full load multiplied with 100. And what about VDC no load? When RL is maximum, the corresponding DC is maximum, which is known as VDC no load. It doesn't mean that RL is infinite. If RL is infinite, the circuit doesn't work. Right? Open circuit terminal, no diode conducts at all. So we should see that the diode is with minimum conduction. There is a current flow, the RL is increasing such that IL is about to approach 0, but not exactly 0. Okay, so VDC no load is equal to VDC with RL maximum. So what it is? It is 2Vm by pi into RL maximum by RS plus RF plus RL maximum. But here what we can write is as RS plus RF, it is very much less compared to RL maximum. I can write VDC no load is equal to 2Vm by pi into RL max by RL max. It is 2Vm by pi. It is approaching, right? V output peak amplitude is approaching Vm, so that VDC no load becomes peak amplitude multiplied with 2 by pi. 2Vm by pi. We can write. And VDC full load. It is equal to the value of DC output voltage with RL is equal to RL minimum, which is equal to 2Vm by pi into RL minimum by RS plus RF plus RL minimum. That's it. So implies the percentage regulation, it is equal to 2Vm by pi minus 2Vm by pi into RL minimum by RS plus RF plus RL minimum by 2Vm by pi into RL minimum by RS plus RF plus RL minimum multiplied with 100. And 2Vm by pi I can cancel both numerator and denominator. Ultimately what you get is RS plus RF by RL minimum multiplied with 100. Final answer. And regulation is also as much low as possible. There should not be much difference between the DC voltage levels with RL maximum and RL minimum. Even though your RL is varying, your output voltage amplitude should not vary much, or your DC output voltage should not vary much. That's what is called as load regulation. Okay, so ideally its value is 0. Practically it should be as much small as possible. Okay, percentage regulation we have seen. And the third parameter is efficiency. It is given by DC output voltage, DC power delivered to the load by AC input power. Conversion efficiency, how much amount of AC is converted into DC. So DC output power, it is given by IDC square into RL, or IDC, it is 2Im by pi whole square into RL. Next, AC input. Earlier also I told AC input in the sense PAC, circuit power. Okay, the power absorbed by all the components of the circuit, AC power absorbed. That is just nothing but IL square into RS plus IL square into RF plus IL square into RL. Power absorbed by RS plus power absorbed by diode plus power absorbed across the load resistor. Okay, or power delivered to all these components. IL means I can even write it like IL square into RS plus RF plus RL. So IL at the time of substitution, what should we do? We have to take its RMS value. What is its RMS value? It is Im by root 2 whole square into RS plus RF plus RL. so that the percentage efficiency, it is equal to 4Im square by pi square into RL by IRMS. It is Im by 2 into Rs plus Rf plus RL multiplied with 100. Okay. So Im square cancel. It is 4 by pi square. Right, and directly I'm writing 81.2 by 1 plus Rs plus Rf by RL. This is the final calculation we can see. In half-wave rectifier, the efficiency is 40.6. Here it is 81.2. Conversion efficiency is improved, like has become doubled. Ripple factor has come down and the conversion efficiency is also improved. Okay. Then next parameter is transformer utilization factor. Fourth parameter, TUF. It is just nothing but DC power delivered to the load by overall input or PAC rated secondary. Actual source power multiplied with 100. Anyway, we know the DC output power. It is 4Im square by pi square into RL. Okay. Then PAC rated secondary means it looks like it is the source power. Generally, what do you expect here? General expectation is it is nothing but Vs into IL we expect. That's what I did in half-wave rectifier. Later, at the time of substitution, its RMS value is Vm by root 2 and IL, its RMS value is, as half-wave rectifier I wrote Im by 2, in full-wave rectifier it is Im by root 2. This is what we generally expect. Expected I am speaking. But if you look at the circuit, source power means see the positive half cycles, right? Let me take during both the half cycles. Okay. So the total secondary voltage is 2 Vs, to be frank. Then is it possible to write 2 Vs into IL, ID1? No, because ID1 is starting here and ending here, but not here. What you need to take is take some source, right? If you have some circuit like this, suppose I have some circuit like this and it is Vs and I is the current flowing. What is the power generated at the source? Whatever the current that is leaving the source, that has to enter it, no? The same I is entering. So Vs into I we write. Okay, the power generated, source power, P source, it is equal to Vs into I. Okay. But is there any such possibility to write here? Similar thing? No. Here the total voltage between the two ends of the secondary winding is 2 Vs and I cannot write it like 2 Vs into ID1. Of course, ID1 and IL are same here. Okay, wrong. Or because positive cycles. Negative cycles, what happens? The same 2 Vs you can see. Right, again it is Vs between these two, again between these two it is Vs and the current is starting here. Right, with respect to these polarities, if I write this also Vs this way, right, total 2 Vs, the voltage between these two is 2 Vs from bottom to top. And that is multiplied with ID2. Is it possible to write it so? No. If the current starts here and ends here, then I can write 2 Vs into ID2. But ID2 is starting here and ending here. I cannot take 2 Vs into ID2 or IL. Is it not so? Then what should we write? You can't write Vs into IL. Okay. Because that is not looking like our regular circuits of this kind. AB, AC or so, DC, whatever it is. As it's not looking in the regular fashion, you can't use it so. Okay, then what should we write? It is looking like a combination of two half-wave rectifiers. You see, positive half cycles, one half-wave rectifier. So, what is the rated power? We know this Vs into ID1, and RMS value of Vs is Vm by root 2, and RMS value of ID1, if you take it so, RMS value of ID1 means it is like this. This is our ID1. Its RMS value is Im by 2. Okay, and similarly, second half cycle, this is another half wave rectifier, and what is its rated power? We have already calculated, that is Vs into IL, but here Vs RMS value Vm by 2, and IL, it is again a half wave rectifier waveform, its RMS value is Im by 2 ID2. Is it not so? Combination of two. So what is your overall PAC rated or source power? You can't take it like this, which is absolutely wrong. And what should we take? It is just nothing but the source power. It is twice the PAC rated half, right? 2 times PAC rated secondary of half wave rectifier. That's it. So it is 2 into, what is PAC rated of half-wave rectifier? We have studied, it is Im square into Rs plus Rf plus Rl by 2 root 2. So this 2 and this 2 get cancelled, and it is Im square by root 2 into Rs plus Rf plus Rl. Then the transformer utilization factor. With respect to the transformer secondary winding, what is the utilization or conversion efficiency? The percentage TUF is equal to 4Im square by pi square into RL by Im square by root 2 into Rs plus Rf plus RL multiplied with 100. It is Im square cancel 4 root 2 by pi square. It is coming around 57.3 by 1 plus Rs plus Rf by RL percent. So with respect to the circuit power, it is 81.2, but with respect to the original source, the conversion efficiency is just 57.3. In half-wave rectifier also, I told the same. Due to switching of the diodes, the source power is not equal to circuit power. Source power is different from circuit power. That's why we are defining conversion efficiency as one term, one parameter, and conversion efficiency with respect to the source as another parameter. That's it. So transformer utilization factor. This is also obtained. Next one, the fifth parameter, it is the peak inverse voltage. Okay, PI. For that, actually, this is our half wave rectifier, sorry, full wave rectifier. Right here, positive cycles, what happens, negative cycles, what happens, we have seen. Now, I'm just taking a particular loop. This one, I'm erasing all this and just considering only this loop. Here, if you take the secondary voltage, right, it is Vs, diode D1, I can write VD1 from anode to cathode and VDD2 from anode to cathode. Okay, you can take either positive or negative cycles, doesn't matter. I am taking during positive half cycles. We are taking. What happens? We know D1 is on and D2 is off. So it almost acts like short circuit and D2 acts like open circuit. Anyway, there is another connection through which ID1 is flowing. no doubt about it. Just for our understanding purpose of to calculate PIV, I'm taking this particular loop. Okay, so if I take this loop equation, what we get here, minus Vs, I'm taking polarities like this, minus plus, right, plus Vd1 and minus Vd2 is equal to 0. And neglecting the drop across the diode D1, Vd2 is equal to minus 2 Vs. Means the secondary voltage, the total secondary voltage can be, the entire secondary voltage can be seen across the diode D2, which is acting like open circuit. It is almost acting like short circuit, and it is almost acting like open circuit. Is it not so? So if you observe the total secondary voltage, it can be seen across the diode D2, which is open circuit. I will just show it as open circuit further otherwise. Okay. So the entire secondary voltage can be seen. Means, right, actually here it is looking like 2Vs. Why? Because one end of the secondary winding to ground, I am taking it as Vs. And the same thing from this point to other end of the secondary winding, it is Vs. That's why it is appearing like 2Vs. Or the entire secondary voltage can be seen across the diode D2. I can say entire secondary voltage. So it is equal to minus 2 Vm sin theta. Then what about the peak inverse voltage? What is the peak voltage experienced by the diode under reverse bias condition? Peak voltage, it is 2 Vm, or it looks like 2 Vm because of the notation we are following. But the entire secondary voltage peak amplitude, right, both ends of the secondary winding, right, that entire voltage is seen across the diode D2, which is not in conduction. That's what is our peak inverse voltage is. Okay, right, done. And finally, the last parameter, it is the ripple frequency. It is the frequency of unwanted ripple. It is just nothing but frequency of output. And output frequency is 2 times the frequency of input. Time period of output is half the time period of input, so frequency will be doubled. Frequency of input. Right? What is its significance? We will see this later. Right? In filters and all, we can discuss much better. At this stage, just we are measuring it. So, in a Sunday tapped full wave rectifier, what we observed is the first one is IDC. It is twice the DC we got in half wave rectifier. Okay, IDC. And VDC also we calculated VDC. It is 2 Vm by pi into RL by RS plus RF plus RL. We have seen. Next, ripple factor. It is better compared to half wave rectifier. Okay, and the conversion efficiency. Anyway, the percentage regulation, it is same as that of half wave rectifier, RS plus RF by RL minimum into 100. Okay, actually, right, doesn't matter. Conversion efficiency, it is 81.2% by 1 plus RS plus RF by RL. Okay, this one only we write, but instead of RL minimum, we just write RL. And the transformer utilization factor, with respect to the circuit, it is 57.3%. And the next one, it is the peak inverse voltage, it looks like 2 Vm, and finally the ripple frequency, it is twice the input signal frequency. These are some observations. Okay, that's it. That's about the analysis of shunt tapped full wave rectifier. Next, we need to do some problems based on what we have discussed.